Now that we've seen the proof of FTC2, I want to go through some examples where we'll actually see it in use. So to start with, suppose that we're asked to find the derivative with respect to x of the integral from 1 to x of t squared. I want to go through two different ways we could do this. So the first approach is going to be to use what we called FTC1. So here, I'm going to work from the inside out. So we look at the integral. FTC1 says we can find that an antiderivative of t squared is t cubed over 3. And we need to evaluate that from t equals 1 to t equals x, which gives us x cubed over 3 minus 1/3. Now, the last step is to take the derivative, and we get x squared. Approach 2 is going to instead use FTC2. So we have the same prompt. In order to use FTC2, I just need to guarantee that my integrand is continuous over my interval. And in that case, I just rewrite the integrand, replacing the variable to be that of the differentiation variable. So I want to point out a couple things. First of all, you'll note that the second approach is in some sense much simpler. There's not a lot of work to show, but beyond that, I want to point out that if this were a different integrand that was much more complex, maybe we couldn't even find an antiderivative from approach 1. So in some instances, not only is the second approach cleaner, it's also the only one that would be possible. And then finally, a very common mistake is I will notice students wanting to involve the lower limit of integration in their answer. And here I should get the same answer, whether that is from 1 to x, 100 to x, or 7 to x. And I'll point out that we can really see in some sense why that doesn't play a role. If you look back at this part here, that lower limit of integration is always going to contribute a constant. And then when I differentiate a constant, that goes to 0. So just be careful about wanting to include that in your answer. So there are instances where we have to do a little bit of work with FTC2. So here I'm going to define g of x to be the integral from 1 to x of square root of 1 plus t squared. With that, let's find the derivative of several things. So first of all, if you're asked to just simply take the derivative of this expression, much like our previous example, I will be able to look at this, apply FTC2 directly, and simply write the integrand as a function of x. But if we were asked to instead take the derivative of the integral from x to 1 of this function, it's significant to note that the statement of FTC2 has the variable in the upper limit of integration and a constant in the lower limit. So we shouldn't expect to be able to just simply apply that directly if we don't have that in our expression at hand. But what I can use is a property of the definite integral to say that this is the same thing as finding the derivative of minus the integral from 1 to x of root 1 plus t squared. So effectively, this would be the same thing as asking you to find the derivative of minus g of x. I'll point out for notation consistency up here, this that we found in part A could be referred to as g prime of x. So the answer down here should be minus g prime of x. And so we would simply get the negative of our answer to part A. The other thing we could potentially run into is if we had to find the derivative of, again, a constant in the lower limit of integration, but some function of x up top. So let's say cosine. So what I want to point out, so we can think about how this relates to differentiation rules, this is the same thing as being asked to take the derivative of the composite function g of cosine of x. So if you come back to our definition of g of x, if I were to replace x with cosine of x, this is what we'd get. When we differentiate a composite function, we need to use the chain rule. That says take g prime and evaluate it at cosine of x, and multiply that by the derivative of the inside function cosine of x. Again, we already know g prime of x from part A is the square root of 1 plus x squared. So if I were to compose that function with cosine, we would get square root of 1 plus cosine of x squared, all under the radical, and multiply that by the derivative of cosine, which is the sine minus sine of x. So to generalize that, if we have a function of x up top, then we get the integrand function, replace the integration variable with our function of x, and multiply by the derivative of that function. And then one last part of this example, suppose we were asked to find the derivative with respect to x of the integral from x squared to x cubed of this same integrand. Again, at this point, we know how to deal with a variable only in the upper limit, a variable only in the lower limit, and now we have both. But we can, yet again, use an integration property to rewrite this so that we can take advantage of that knowledge. This is the same thing as taking the integral from x squared to any constant, I'm going to choose 0, of the integrand, plus the integral from that same constant to x cubed. And now we can see that this would be the same thing as taking the derivative of negative 1 times the integral from 0 to x squared of this expression, plus the derivative of the second integral. And in our final step here, we want to make use of the chain rule, much like we did in part C. So this should give me minus the square root of 1 plus the function x squared all squared times the derivative of x squared plus the square root of 1 plus x cubed squared times the derivative of x cubed. So putting that all together, we get minus 2x, square root of 1 plus x to the 4th, plus 3x squared times the square root of 1 plus x to the 6th. And for one last example, I'm going to come back to the notion of what an antiderivative is. So for this, suppose we're asked to find a function g of x such that g prime of x is equal to e to the minus x squared, and also that g of 2 is equal to 3. So the hard part about this is that if you try to come up with a function in terms of elementary functions such that its derivative is e to the minus x squared, you're not going to be able to find one. So this is not the same thing as asking you to integrate e to the minus x squared. We simply just need to write down a function that has these two properties. Based off of what we've seen so far, I know that I could write down the integral of e to the minus t squared if I were to evaluate that from some number, let's say a, up to x. The function I've written here satisfies this first condition. If that were my guess here, let's think about what happens when we plug in 3 or 2. We need the function to evaluate to 3. But right now, we would get that it's the integral from a to 2. But we get to choose the constant a. And we talked about the idea that we can try to think of when it is easy to evaluate something like this. And in particular, we said that if the upper and lower limit are exactly the same, that's the one instance that we should always be able to evaluate this function. So my update here is to choose to make that lower limit of integration 2. So I'm updating my function now to the integral from 2 to x of e to the minus t squared. This still satisfies this first condition. The advantage we have here is when I plug in 2, I at least get a definitive answer. We're integrating from 2 to 2, so that gives us 0. So it hasn't quite satisfied this last condition, but now I'm one step closer. So when I want to write down a suitable function, g of x, remember we talked about antiderivatives, that we can choose any additive constant, and in particular here, we knew that the guess when I had simply the integral from 2 to x of e to the minus t squared dt, that would give us g of 2 is equal to 0. So let's add the constant 3, and now we see that this satisfies this first condition still, but also when I plug in x equals 2, I get 3. So then the idea now of writing down an antiderivative, we can expand it if we start to think about this idea about the relationship between the integral of a function and its integrand.